Afternoon, good evening, everybody. Welcome to week 8 of our focus program. We start this week with the mini course of Dan Timotin on the Branges-Rovnyak spaces. Dan, please.
Okay, thanks a lot, Javad. One moment, I still have some problems here because I have some other windows over. Okay, now I think it's quite fine in this moment. One moment, so can we? Okay. I have a small problem in this moment, so okay, that's fine. Yeah. So thanks a lot for the organizers for inviting me to do this presentation. So there have been a lot of courses devoted to function spaces up to now in this workshop. So I will just put a first page with the things that I want to remember, to remind you. These are usual notation that have been used several times up until now, so there's nothing special. The backspaces will usually, I just write LP because I have normalized the back measure on T, except at some point in course number 3. But up to that moment, it will be the usual, the backspace. And then the Hardy-Hilbert space, you know what it is, H infinity, the algebra of bounded analytic function, on which we have operators of multiplication. And then the norm is the same, remains the same. And the Toeplitz operator has this nice property that this, even if it's a compression of the multiplication operator, it still has the same norm as the infinity norm of phi. The formula that's the n t phi star equal t phi bar will be used repeatedly in the courses. Okay, if phi is in H infinity, then we don't need the projection. The multiplication operator just leaves the space H2 invariant. So we just have T phi f equal phi f. The usual notation for the shift operator is Tz. So S would be the shift operator on H2. And its adjoint, again, it's the adjoint in H2 is defined by the well-known formula f of z minus f of 0 divided by z. So I think this is more or less what I have to remind you. Then we'll see during the course if there's something else. I'm trying to be as self-contained as I can. So I start with a little bit of history. The spaces we will discuss have their origin, as I said, in 2 works published by the Branges-Rovnyak in 1966. There's a book, Square Summable Power Series. And then there's an article in the Proceedings collection of a conference that had taken place in 1965 in Madison. And well, you see the title of the collection. In fact, what we are interested now, what we will be talking about is contained in the appendix to this article. In the first part, there are some other spaces of entire functions that are considered. Now, what is the purpose of Rovnyak here? They try to obtain functional models for arbitrary operators on a Hilbert space. What does this mean? It's very simple. We are given an abstract class of operators, A, frac A, and we want to find a smaller subset, A prime, of operators which are concrete operators on a certain Hilbert spaces of functions, and for that matter, they are spaces on the unit disk, such that any operator in A is unitary equivalent to an operator in A prime. So if we want to study the operators in A prime, we may do it by looking at their model in A. Now, what were the operators? The class A of operators. Any contraction, this is usually called the Langer lemma, any contraction on a Hilbert space can be decomposed as a direct sum of a unitary part and the completely non-unitary part. The completely non-unitary part, well, as its name shows it, means that you don't have any subspace reducing or invariant subspace, because it's the same in this case, on which the contraction would be unitary. The philosophy was, of course, that the unitary part is well known because of multiplicity theory and spectral theorem. And so you want to get a model for the completely non-unitary contractions. This was the purpose of the Branges-Rovnyak. Well, in the two papers that I know that I wrote before, they managed to do this, but somehow there is, let's say, bad luck that in the same time there was developed the Nock-Voyage theory of contractions, and the models in the Nock-Voyage theory are basically equivalent to the Branges-Rovnyak models. It's just another way of looking at things and another way of describing things, but somehow it had more success. It was more easily, well, understandable, let's say. It's a more geometric model. And so in the next years, basically, I think few people looked at the Branges and Rovnyak work. Afterwards, in the 80s, these spaces has begun, I think there is a typo, sorry, to be studied as independent functions, especially in a series of papers by Donald Saracen. I think Saracen writes somewhere that he began to be interested in these spaces after having a talk with the Branges. And most of these results have been gathered in this nice book, Sub-Hardy Hilbert Spaces and the Unit Disk, very concentrated, but which contains a lot of things about these spaces. And actually, I think most of the content of my course can be found there. Well, after these papers of Saracen, the spaces have begun to attract interest. And so there's a number of persons that have worked on them, and I put here a series of names, and I'm very sorry if I missed somebody, and I surely missed somebody, I'm pretty sure, but well, this is just informatively. Okay, and let's finish by saying that all these works up to 2016 have been gathered in a big comprehensive treatise of Emmanuel and Javad, 2 big volumes. But HMB spaces are only in the second, so you don't have to study more than 800 pages if you want to see what happens with HMB spaces. Okay, so I think this is about all history. And I start now to get to the spaces themselves. There are several ways of introducing them. And the way I will do it at the beginning will be by considering them as reproducing kernel Hilbert spaces. I think there is also a course that Javad gives on Mondays on this subject. So what I'm right here, I guess most people know, but again, I have to remind you all these things. So we have a Hilbert space of functions such that the point evaluations are continuous. And if they are continuous, they have to be represented by a vector. And the vector is denoted kw. And we usually have this alternate notation. Either we look at k as a function of two variables, z and w, or as the function of one variable, z, corresponding, reproducing the value in the point w. Now, the classical stuff about RKHS says that such a function, if you are given the function k of zw, it is a reproducing kernel of a space if and only if it is positive definite. Now here it's a little bit unfortunate, the way that the name is settled in. Well, the function is you can construct by taking k of zi zj is positive semi-definite. Well, that's life. This is somehow established, well established. So I will say function positive definite, although the matrices are just positive semi-definite. Now I have some properties that also are part of the basic theory of RKHSs. And all you have to do, it's clear that you can't do anything else with these properties. You have to work to try to show positivity of some matrices. So the product of two K1 and K2 is also positive definite because the Schur product of two positive semi-definite matrices is positive semi-definite. Now, this is a focus program on analytic function spaces. So the spaces in which we encounter are usually, because they are spaces of analytic functions, point evaluations are continuous, so they are RKHS. Now, I guess in most of the previous courses, the reproducing kernel appeared, but I will just make a list of them. So H2, the Hardy space, has as a reproducing kernel the Cauchy kernel. The Bergman space is the square modulo some constant. Well, I have ignored the constant that appears here. Usually, if you want to get the some precise norm, you have to play with the constant. The Dirichlet space has a reproducing kernel a little bit more complicated. And what interests us mostly are the model spaces that have been the subject of Stefan's course. And they have they are defined by the formula H2, the orthogonal complement of UH2 in H2, where U is inner. And they have the reproducing kernel 1 minus U of W bar U of Z over 1 minus W bar Z. Now, let's have a little bit more properties of RKHS before we are getting to our work with the Branges-Rovnyak. There is a kind of trivial example of kernel, namely, if you take a function of a single variable and you form the product phi of Z phi of W bar, then it's positive definite. It's a simple formula there. So since we know that the product is of two positive definite functions is positive definite, we can multiply a given kernel by phi of Z phi of W bar. Now this is something a little bit more complicated. If we take the difference of two kernels and it happens that it's still positive definite, you have this bit of luck, then this is equivalent to the fact that H1 is included in H2, and the inclusion is a contraction, which is what I wrote here. So this I will often say is H1 is contractively included in H2. Okay, now one more result from the general theory. Again, we have two kernels, and we form their sum. This is again a reproducing kernel. The space is the sum of the spaces. If we assume that the intersection is 0, then the norm is given by this very nice formula here. And in fact, this is the only case that we will consider, or we'll have to consider. If the intersection is not 0, then you have to, as you can imagine, that you have to take all possible decomposition for the same function as a sum of two functions and take the infimum of the norm. Okay, now such a space comes with the algebra of multipliers. And a multiplier, it's quite natural. It means that if we multiply a function of h, then we still are in h, and then the operator is bounded on h by the closed graph theorem. I have a different m here because I wanted a bold m because I wanted to keep the usual m for multiplication in L infinity. This is a general multiplier. Now, some of the properties of the multipliers, if one belongs to the space, then the multipliers are contained in the space. This is quite trivial because we apply multiplier to 1. Now, this is a very nice property that probably everybody has to do it once in its life to do the computation, namely that the reproducing kernels are eigenvectors of the adjoint of multipliers, and the eigenvalue, there's a typo here, it should be phi of w bar. So okay, let's see. No, I don't. As an immediate consequence, the supremum of phi is smaller than the norm of multipliers because it has already these eigenvalues. Now there are a bunch of cases when you have equality here and another bunch of cases when you don't have equality. In our situation, usually we don't have equality. So we have to be careful. This means that we cannot check whether we have a multiplier just by looking at the values. But we can check, we have a result that tells us when we have a multiplier of norm smaller than 1. And again, it's a question of some function that has to be positive definite. Well, about whatever you do with reproducing kernels, you have to check that some function is positive definite. And in this case, it's this function. Okay, so I think I'm done with the general. So let's go to the Branges-Rovnyak spaces. And the way I will introduce them is starting from the reproducing kernel of the model spaces. Usually in my notation, U will always be an inner function. So model spaces correspond to inner functions, and the kernel is this one. Now, suppose that instead of considering U, we consider a function B in the unit ball, but which is not necessarily inner. Is this a positive definite function? It's a natural question. When you just look at it, it doesn't necessarily look like a positive definite function. But actually the answer is yes. It's a good thing that the answer is yes. So I'll state it as a theorem. This function is indeed the reproducing kernel of a certain space that will be denoted h of b. And moreover, h of b is contractively included in H2. So this, in fact, as I said, means two things. First, that it is a submanifold of H2. which just looking at the kernel, there was no special reason to say. And moreover, the norm is larger than the norm in H2. Okay, and this is called the Branges-Rovnyak space associated to B. Well, let's prove this fact, this theorem. As a general strategy, I will give some proofs when they are not too complicated, of course. If they are too complicated, then you have to look the references. But I think it's good to give some of the proofs if you are allowed by time. Okay, so in this case, it's very simple. You have this function of infinity norm smaller than 1. So multiplication by B is the Toeplitz operator TB. And we know that the norm of the Toeplitz operator is smaller or equal than the infinity norm of B. This is a function, it's related to H2. It's not a general fact, of course. But now we remember the general fact. And we state this in the language of our Vincent kernel Hilbert spaces. This means that B is a multiplier of H2 of norm smaller or equal than 1. And we had a little bit earlier here at the bottom of the page, we have the condition that a function phi be a multiplier. So we apply it here and we get the kernel we are interested in. So it is in kernel Hilbert space. Now, if we want to show that it's contractively included, we have to use the other property, namely we take the difference of the two kernels. And of course, it's again a positive definite kernel because it's the trivial kernel multiplied with the Cauchy kernel. Okay, so the conclusion is that the inclusion is a contraction. Well, unfortunately, at this stage, if we don't know more about the space, we cannot even give many examples to somehow to have a feeling. How look these spaces? We have the example we started with, inner function, then we get the KU, which is the model space. And then we have a very trivial example that if B is 0, then of course the kernel is just the Cauchy kernel, so H of B is H2. But for the moment, we don't have other examples. We don't have, in the sense, of course, we can take some function B, but if I were to ask you whether a given function is in HB, you don't have a way to answer. So the moral is that I have to obtain another way to characterize these spaces. This reproducing kernel matter, it's very nice to begin with, but then if you want to work, you need a little bit more. And indeed, what we will do, there is an alternate description, and this will be done in terms of range spaces. Now, in general, a range space, well, we will, a few points, a few general points here. We have a contraction between Hilbert spaces. We could define, of course, the range also without being a contraction, but in our case, it will always be a contraction. We denote by M of T the range of T, but not only as a subset, as a set, but we give also a norm on it, and we want to obtain a Hilbert space. And the norm is defined by, in case T is injective, is 1-to-1, then the norm of TF, which is an element in M of T, is by definition the norm of F. And the scalar product is by definition, the scalar product of TF and TG is by definition the scalar product between F and G. So I look backwards where the function, where TF comes from, and I take the norm there. Now, if I put it this way, you understand why I said T is injective, because if it's not injective, then I have a problem. I might have several G's which go in the same element in M of T. And in this case, the norm, the formula for the norm is a little bit more complicated. It has to be defined as the infimum of their norms. But usually it's simpler, instead of taking the infimum, just to restrict T at the orthogonal of its kernel. So it's injective, and then I can use the formula that I have given. This is in fact the reason why I was a little bit vague here, saying T is a contraction between two Hilbert space, because if I prefer to take to restrict the domain. What is important is the range, in fact, because the range has to remain the same. Okay, now there are some variations. I said variation on Douglaslemma. Actually, the first item here is exactly Douglaslemma, that says that M of T1 is contractively included in M of T2 if and only if you have this inequality of positive operators. So again, contractively included means that you have an inclusion and the norm, one of the norm majorizes the other. And a very similar situation happens if I want to have a condition for T2 to act contractively on such a range space. Namely, we have this inequality, again, an inequality between positive operators to be satisfied. Well, so once we have these tools, these variations on Douglaslemma, we can come back to our we'll have a more general lemma. I take T with values in H2 and injective. Then M of T is a reducing kernel Hilbert space. And I can write precisely the kernel is TT star times the Cauchy kernel in H2. And the proof is very simple. I have written here, it's 2 lines. You just check that indeed, if you multiply a TF with TT star KW in M of T, you can do this easily because you have T before the 2 elements. So you can write it in terms of the 2 norms. And in the end, what you obtain is exactly TF of W, which is TF scalar product in M of T with a reproducing kernel there. So the 2 right-hand side have to be equal. Okay, so let's see what happens this in particular for the Toeplitz operator corresponding to a function B of norm smaller or equal than 1. Well, it means that I have to compute TB star KW. Now I know that if I apply the adjoint, this is an eigenvector with the eigenvalue BW bar. And if I apply TB, I have just to multiply because these are analytic functions and there's no need of a projection. So the result is precisely the Cauchy kernel multiplied with what we call the trivial kernel, B of Z, B of W bar. Okay, now what is more interesting, because we are mostly interested in H of B, and the M are more like tools that we use in order to arrive at M of B. H of B is the range space corresponding to I minus TB star 1/2. This is usually called the defect space, but I try not to introduce too many words. And again, the proof is very simple. We consider this operator as acting from the closure of its range into H2 so that it is injective. As I say, that's the little trick of restricting to the orthogonal of the kernel. But this being a self-adjoint operator, it's the same, the orthogonal of the kernel is the same as the range. And the previous lemma tells us that I have to get the reproducing kernel, I have to take kw and multiply it with this operator times its adjoint, but its adjoint is itself since it's positive. So I just get I minus tb star kw, which is precisely kbw. I don't remember if I have formally introduced this notation, but kbw will be 1 minus b w bar b of z over 1 minus w bar z, the reproducing kernel of the Branges-Rovnyak space. So that's nice. I obtained another way of describing H of B as a range space. And this is better in the sense that we can prove more. The first example, we already have had them, but let's see what it becomes in this context. In this context, the defect operator here is just the orthogonal projection onto Ku. So of course its range is Ku. And moreover, the norm is the same. So there is no change of the norm. You have seen that usually when I have norm of Tf in the range space equal norm of F in the original space, it's a different norm. But in this case, and in fact only in this case, we get the same norm. But now we can give another example, which is a little less trivial, let's say. We take a B that has infinity norm strictly smaller than 1, then the defect operator is bounded below, and you can easily see that H of B is a renormalization of H2. So the norm is in fact equivalent. The image is the same and the norm is equivalent because the operator that appears here is invertible. Okay, now this is a kind of philosophical comment. In both approaches, the definition is a little bit elusive. We cannot say, okay, so to check that this is a function in the space, I have to show that this integral is finite, or so I have to estimate it, or some sum of the Fourier coefficients. So it's a little bit harder. It's still not very clear how we can put our hands on the space. Okay, so I thought that it's a good thing to give a non-trivial example. And I take the function b of z 1 plus z over 2. This is an example that will appear again in the course. But this is here, I want to discuss it somehow at the beginning without knowing too many general things of the Bronzerovnik spaces. Okay, so my function is a function in the unit norm, and as you can see, it has infinity norm 1. So we're not in the trivial case that I discussed on the previous slide. Now, if we take phi of z equal 1 minus z over 2, we see that if we, so I take this kernel, I multiply the Cauchy kernel with phi of z, phi of w bar, and I get the kernel. I already did this, that if I multiply with TA or T something, then I get the reproducing kernel of the range space of T phi. And this means the range space of T phi. This means that it's you have the family of all functions of the type 1 minus z over 2 H2, and the norm is the range norm, so it's given by the norm of G. Okay, now this is point number 1. Now, point number 2 is that if I change a little bit the norm of a complex number to be 1 over square root of 2, its usual modulus, then C becomes a producing kernel space with this constant kernel. Now, why did I do this thing? Because I want to do a little trick now. I want to add these two kernels, K1 and this. And then the sum of the kernels happens, as by miracle, to get exactly the kernel of my Branges-Rovnyak space. But I know that there was a general theorem before that said that this means that the kernel is that this is the kernel of the sum of the spaces. So H of B is the sum of these spaces. Now I've changed a little bit. You see, instead of 1 minus z over 2, I put just 1 minus z, because this amounts in having a slightly different norm. The two terms are orthogonal because the intersection is 0. That theorem, that general theorem, told us that the norm is given just by the usual formula. The two terms are orthogonal, so I have the Pythagoras formula. I put here similar because of these constant that make, so you have equivalence here. So we know, in this case, we know what is H of B, is the sum of these two things. And I will show a little bit a certain number of properties of this space. First of all the functions have radial limits in 1, because I know an estimate for a general function in H2 when you go on the radius to a boundary point. And so the limit of this function is just C. H of B is dense in H2. If F goes through all polynomials, then C plus 1 minus ZF also goes through all polynomials. This is easy to see. But of course, H of B is different from H2, since not all functions in H2 have radial limits in 1. Multiplication by Z, the shift operator, leaves H of B invariant as a manifold, and the restriction is bounded. I made here a little bit of computation. I multiply by Z, and I have to rewrite it in the form constant plus 1 minus Z something, and I get the norm here. But be careful, it's not an isometry anymore. In fact, it's not even power bounded. And this is again a funny computation. You apply multiplication to 1, you get Z to the n, but if you want to write it as C plus 1 minus ZF, you have to write it like this and take the H2 norm of this sum, and the H2 norm of this sum is square root of n. Okay, so I think this is quite an interesting example, because it shows a little bit the kind of things that you can expect in the Branges-Rovnyak spaces. Now we are coming back to the general case. And first of all, we have already seen that in the case B is inner, I get the model space, which is a closed proper subspace. But in fact, this is the only case when H of B is closed. In all the other cases, it's dense in H2. Well, no, I have also, for instance, 0, or the case when the norm of B is strictly smaller than 1, when, of course, it's equal to the whole H2, so it is closed. But in any case, in all the other cases, H of B is dense in H2. And why does this happen? Well, it's again a little computation that I can afford to do it. We have to show that the kernel of this operator is 0. And this is a simple computation. If F belongs to this kernel, then you apply I minus TB star F, and you take the product with F, you get 0, and this is written like this. So if you go to integrals, you obtain this inequality. But since B is of modulus smaller than 1, in fact, you need to have 1 minus b squared f squared equals 0 almost everywhere. And in case b is not inner, f has to be 0 on a set of positive measure, which implies f identically 0 by the Rees theorem. Okay, now let's see some other properties in the general case. Today we will do the general case, and you will see that tomorrow, in fact, there are two very different types of the Branges-Rovnyak spaces. So I use the same notation in the case when phi is not analytic, because there is this space H of B bar is quite important if we want to study H of B. And the properties that I discuss now is that this is contained contractively in H of B. And it gives a way of, an alternate way of checking whether a function is of H of B and computing its norm. Take a function in H2, then it's in HB if and only if TB bar H is in H of B bar. And in this case, the norm is precisely, it's given by a Pythagoras formula, which involves the 2 norm of H and the H of B bar norm of this one. And finally, if phi is in H infinity, this is quite important, then H of B is invariant with respect to the adjoint of any Toeplitz operator, any analytic Toeplitz operator, and the norm of the restriction is at most the infinity norm of phi. So this is of course true for the case of, for the H2 case, but here we are working with different norms. So whenever we have a nice property like this, we have to be grateful. Okay, I thought to do the proof here, and probably of 1 and of 3, yeah. Contained contractively here, fortunately, we have a formula with the range spaces, the Douglaslemma. And so 1, the contractive inclusion of H of B bar and H of B is equivalent to this. But now this inequality is equivalent to the fact that TB is hyponormal, as operator theorists say. But this is a very simple computation. One knows that Toeplitz operators are hyponormal. So in fact, H of B, this is the computation that proves it. And so H of B is contained contractively in H of B bar is contained contractively in H of B. Now, the second part, I will not, well, in this case, this is the second part, and I will not prove it because it's more complicated. And of course, it's not very nice to give long proofs during a Zoom presentation because you expect nobody to follow. However, let's see what happens if U is inner. Then H of U bar is 0 because it's 1 minus TU star TU, and TU star TU is 1. It's an isometry TU. So we obtain that H is in KU if and only if TU bar H is 0, which is exactly the fact that this is precisely satisfied by the functions in the model space. And this second term in the norm is 0. So the norm is the H2 norm. Okay, now let's try to prove the invariance of H of B with respect to T phi bar. The first step is to prove that T phi bar acts contractively on H of B bar. And this, again, we use the type of the Douglaslemma. We have to check an inequality between positive operators. Now we rewrite it, and after a little bit of rewriting here, what we obtain is precisely T of the symbol 1 minus B squared 1 minus phi squared. Well, but this is a positive symbol, and then it's the operator itself. It's called positive because it's the compression of the multiplication operator. Okay, now why does it act contractively on H of B? Well, we take an H in H of B, we apply point 2, the one that I have not proved, and but if H of H belongs to H of B implies that TB bar H is in H of B bar. And by what we have just been proved, this space is invariant to H of B bar. So we get this relation and we apply again point 2. We have that TB bar T phi bar H is in H of B bar. So the T phi bar H belongs to H of B. So it is indeed invariant. And the fact that it acts contractively, it's a simple computation using the fact that we have this formula for the norm. And T phi bar acts contractively both on H2 and on H of B bar. Okay, I think this is the longest proof that I will present. I hope that you are still have patience. Now, what is the important thing here is that, the most important thing is that H of B is invariant under S star. And this is, and this operator, the restriction of S star is a contraction. This is somehow the model operator in the case of the Branges-Rovnyak spaces. So since H of B is not invariant with respect to S, the adjoint is not at all S, so we don't have to expect this. But we have a formula for the adjoint that uses S. And well, we have to, maybe I will, because I want to finish something else, I will go quickly through the proof because, well, there are just some computations. And let's describe some inhabitants of H of B. First of all, the reproducing kernels, of course, they are there. At least this is what you know about any reproducing kernel Hilbert space, that at least the reproducing kernels are inside. Now, for an antifunctions, if you take the derivative in some W, it's also a bounded functional, so you have its representing vectors belonging to H of B. We will not use them too much. Now, S star B is always in H of B. Remember the result that we had, point 2, that I did not prove, that said that something is in H of B if and only if we apply T of B bar, we get something in H of B bar. But if we apply TB bar here, what you get is this thing. And you know that 1 minus TB bar TB applied to 1 is an H of B bar. And I know that H of B bar is invariant to S star. So this belongs to H of B bar and S star B belongs to H of B. B itself usually does not belong, but we'll come back to this. Now, there's a nice operator formula that you can check that if you apply to S star B, that is in H of B, this resolvent of XB, you get precisely the formula for the difference, well, the difference quotient formula, as it's sometimes called. And so also these functions belong to H of B. And the last thing is that we have a function in H of B, and we factorize it with an inner function, and G, which is obtained by applying T of U bar to F, is also in H of B. So in particular, the outer part of a function always belongs to H of B. Okay, so I still have to discuss the last thing that I want to do today, and I hope it will not take more than 2 minutes, is the behavior of the boundary of functions in H of B. There's a general principle that has already seen in the model spaces in the course given by Stefan, that on T, on the boundary, the behavior of B in some sense determines the behavior of functions in the whole space. Now, what does this mean, to be more precise? Well, I will give you two instances. First of all, analytic continuation through an arc. So both these results are an extension of what happens in model spaces. So probably you have already met them there, but it's interesting that they are still true in the case of the Branges-Rovnyak spaces. First of all, whenever we have an open arc of the circle, then the two things are equivalent. B has an analytic continuation across I, and modulus of B equal 1 on I, and the fact that each function has an analytic continuation across I. Now, you see, it's interesting that in the case of inner function, we don't need to add modulus of B equal 1 because they satisfy this. But in this case, we need this second condition because otherwise, you see, we take B equals 0, it's analytic across any arc, but the space is the whole H2, so you don't have such a property. The second property is what happens in a point. We have we take again B in the unit ball, a point in the boundary. Now, the following are equivalent. If we just look at B and we see that B and B prime have non-tangential limits and the modulus of this limit is 1, then all functions in H of B have non-tangential limits. This is usually called that B has an angular derivative in the sense of Kara-Fiodori, but I don't want to do this. And in this case, because all functions have non-tangential limits, then this means that somehow we can define the value in zeta. And this happens to be a bounded functional, and it has as a reproducing kernel precisely the reproducing what we obtain from the reproducing kernel if we replace a W in the disk by a zeta on the boundary. Okay, so let's finish with this example revisited. This satisfies the condition for zeta equal 1. It has B and B prime, of course, they are simple function, they satisfy, but also in 1 we have B of 1 equal 1. And we have already noticed that a function in that space, in H of B, has non-tangential limit in 1. So that was a particular case, a very particular case of this general result. So for today, I'm finished. Thank you.
Thank you indeed, Dan. Let's thank the speaker. Wonderful talk. Is there any question or comment for Dan? Indeed, Dan, in the previous slide, I missed something. You said something about B identically equal to 0. Could you please go back there? Here. Simple.
No, I just wanted to point out the fact that you need the condition modulus of B equal 1.
Yes, unimodular is essential.
Mm-hmm.
Any comment or question for this lecture? If not, let's thank Dan again.
Okay.